In this video, we're going to do a more advanced example of expanded octets. We're going to follow the recipe, and it's going to give us a structure that looks okay until we check the formal charges. The formal charges on the structure we're going to get are high. And there's a way to fix high formal charge structures when your central atom is a very large atom. You can try expanding the octet on the central atom, and it gives you a better structure. Alright, let's build a structure for, do you remember what this one was called? ClO3 minus was chlorate ion from your polyatomic ion list. This has got one more oxygen atom than chlorate. So you put a per in front of the name. This is perchlorate ion. Let's do a loose structure for this. Let's follow the recipe that we've been following. Step 1, draw a skeleton structure. Okay, that puts the atom that is closer to the center of the table in the center of the structure. Now, this kind of a little iffy, I guess. Which of these two are closer to the center of the table, the O or the Cl? I would say the O is on the edge of the table, so I'm going to try and put the Cl in the center. Often the way people write the formula for something gives you a hint about what the central atom is going to be. Cl, chlorine, comes first in the formula, and very often in these formulas they'll put the central atom first. So that's another hint about the right skeleton structure. So there's my skeleton structure. Step 2. Count the valence electrons. Okay, I'm going to look at chlorine on the periodic table. It's here, and it's in the column with 7 valence electrons. So I have 7 for the chlorine, plus 4 times what for the oxygens? Oxygen is in the column with 6 valence electrons. Is that all? Is there something I'm forgetting? Yes. I'm forgetting the minus sign that's on this. I have to add an extra electron on for that. So what do I have here? I've got 7 plus 24 is going to give me 31, and then one more is 32. So I have 32 electrons to work with. Okay, number 3. Connect the structure. Okay, here's my skeleton structure. Let's connect it. Connecting it draws a stick between the central atom and each outside atom. That cost me 2 electrons per bond that I drew. So that's minus 8. So what do I have left? 24, right? Okay. So the next step is to satisfy the outside atom. Now, here, let me copy the structure over again so you can see how I'm building it up step by step. Now, each oxygen has already got 2 from the bond. It wants 8. It wants an octet. So it wants 6 more. So let's count out electrons that we need. 1, 2, 3, 4, 5, 6. That one's happy. 7, 8, 9, 10, 11, 12. That one's happy. 13, 14, 15, 16, 17, 18. That one's happy. 19, 20, 21, 22, 23, 24. I took away 24. I have none left. Okay, the 5th step. Dump your remaining electrons on the central atom. Alright, well, I don't have any remaining electrons, so there's nothing for me to do there. Is it satisfied? Now, it looks like it is. It looks like it's got an octet. So I'd say yes, and then I'm done. And if I was a B student, I'd probably stop here. I'd be happy. I'd write this down. And of course, to finish it off, since it has a -1 charge on it, I would lose a point if I didn't put square brackets around it and put a minus sign on it. Now, if you gave me this on a test, I would probably give you, and it was worth 5 points, I would probably give you 4 out of 5 points on that. I'd give you like an 80% on that. You followed all the rules. You did everything right. Well, sometimes you can follow all the rules and things are not as good as they could be. And that's the case right here. Oh, if you're a student, you're always going to be applying step 6, even if it looks like you've got a good structure there and you're done. Step 6 is find the formal charges. You always got to check those. So let's check them here. And we'll see that there's a problem with this structure when we do. Okay, check out the charge on any one of the oxygens. Now, if you look at those oxygens, all 4 of them are identical. So I only need to assign formal charges on one of them, and then I know the formal charge on all the others too. Oxygen has got 6 valence electrons on the periodic table. See? And then minus the number of sticks and dots that are around it. That's the formal charge. 1, 2, 3, 4, 5, 6 dots, and a stick is 7 sticks and dots. So the formal charge is -1 on each oxygen. So each of these oxygens has a -1. That's a lot of formal charges. How about the chlorine? The chlorine in the center has got 7 on the periodic table. There's chlorine, 7. Minus how many sticks and dots? There were 4 sticks around it. Plus 3. So you have a +3 charge. It's a very high formal charge. Very high formal charge on the chlorine that's in the center. That's no good. This is an awful structure. The rules work most of the time, but not all the time. There are times when the rules are going to lead you astray, and this is a case where that has happened. How do we know that we haven't gotten a good structure? The formal charges are the only way. They're the only thing that would tip us off to the fact that this is not a good structure. So the moral of the story here is always assign the formal charges in the end. Like I said, I'd give you 80% on that structure. Let's be an A student. Let's get 100% on that structure. Here's how you can fix it. The first thing I notice is that this is kind of a cry for help from this chlorine. It says, I need more electrons. All right, if I had 3 more bonds, I'd be happy. That's what this says. And these oxygens are saying, well, I have too many. I have a lone pair too many. I can share that as a bond. And each of the oxygens is saying that. The chlorine is saying, I need you to share 3. And the oxygens say, well, we each can share 1. So that's the basis for this adjustment of the structure that we can do. If I write the structure down again, and I say, well, let's do a structure where this one shares. The chlorine, since it had a +3 charge on it, a +3 formal charge, we want to share 3. How about if I do 1 from here, 1 from here, and 1 from here? See if that helps. So I'll get a structure now that looks like this. I could never think about doing this unless this was a third period or lower atom in the center. You could not do this with fluorine. Fluorine just will not form an ion like this. So I get an ion like this. Now let's figure out what the formal charges are here. Alright, 6 for oxygen minus 1, 2, 3, 4, 5, 6 is 0. So all of these oxygens that have a double bond going to them have a formal charge of 0. How about this one? 6 for oxygen minus 1, 2, 3, 4, 5, 6 sticks, and then a dot is 7. Minus 1. So there's a minus 1 charge on that. How about the chlorine? Chlorine on the periodic table has got 7. Minus how many sticks and dots? 1, 2, 3, 4, 5, 6, 7 sticks. It's got a 0. Now look at how much better this structure is than the structure that we had in the beginning. The structure we had in the beginning had a formal charge that was fairly high on each atom. This one, the formal charges are 0, except on this one atom. And you're not going to get them all to be 0 ever, because all the formal charges need to add up to the charge, the total charge that you've got on the ion, which is minus 1. So 0 plus 0 plus 0 plus 0 is plus minus 1 is minus 1. And this is as good as you're going to get. So this is a much better structure. This is an A student structure. But wait, you don't get your A for this structure yet until you realize this. Why did I just pick these 3 neighbors to share? In fact, any group of 3 neighbors can share. So this is just one of several resonance structures. I had these 3 neighbors share. What if I had these 3 neighbors share? It would look like the same structure with the single bond going up this way and double bonds going out like this. We can't be lazy. We have to write the entire structure in here. So here's one resonance structure, double arrow. Here's a second resonance structure. Now I can put the single bond down here and the single bond here. That is the third and the fourth resonance structures. So I have 4 structures to tie together. If we put the single bond going down this way, we're going to get this one. Notice all the resonance structures look kind of the same. It's just that you're moving where the single bond is. The formal charges on all of these resonance structures will be identical. The last one is got the single bond going down that way. Now, I'll take points off. I'll take a point off anyway if you don't draw all the resonance structures in. Seems kind of mean because this is very tedious, but let's remind ourselves why I am being a stickler about that and why everyone in real life is too. If I look at any one of these bonds, it looks, if I just took one of the structures, it's got double bonds in some places and single bonds in another. And I would expect, if I looked at the bond lengths, these bonds to be shorter and stronger than that bond. So there would be one longer, weaker bond and 3 shorter, stronger bonds. But when I look at this in real life, in fact, the 4 arms, the 4 bonds that are coming out of the chlorine, all have the same strength and all have the same length. So if I look at this bond, say, it looks like a single bond there, but it's a double bond here, a double bond here, and a double bond here. So it is 3 times a double bond plus 1 times a single bond And if I average that over 4 structures, I get 6, 7 fourths. It's a 7 fourths bond. All right, so it's almost a double bond, but not quite, right? It's like a 1 3/4 bond. That's another way to write that. And it's telling me that this bond between the chlorine and the oxygen in the actual perchlorate ion is going to be, it's going to be stronger than a single bond and weaker than a double bond. And you have to write all 4 of the resonance structures here.